I'm Apoorva. This is my website, my Twitter handle. I actually worked in Hyderabad, not far from here, at Microsoft as an intern. Then I worked in NVIDIA from Pune. I am from Pune. Then I moved to Copenhagen and worked for Playdead, where I did a lot of graphics programming. And then currently I work at Unity as a graphics programmer as well. I'm sorry to folks from here who might not see some of the slides, but there's diagrams in there that I think are important, but maybe I'll share the slides later. So basically, today we're going to look inside the GPU and kind of build a better image of what happens inside the GPU when you're rendering triangles or geometry. I'm going to blaze through this talk because I have a lot of topics to cover. So I hope we get time for questions and answers afterwards. But anyway, so most people have like this picture of a GPU in their head if they are working with graphics, which is there's a CPU, there's a GPU, and there's some kind of interconnection between them. And maybe you know that there's like an 8 GB GPU or whatever, so it has some VRAM and so on. But people don't know what's inside really a GPU. So from this, we're going to build towards an intuition that looks more like this. That's a very complex picture. By the end of this talk, we'll cover most of the logical units in here. And at the bottom, you see the logical graphics pipeline as well, which is what you see when you open up RenderDoc or other graphics programming tutorials. And what we are going to see is how this logical pipeline maps onto this physical hardware. And this is a bit of like black magic. It's not very well known, even among graphics programmers, how this stuff works. So having worked at NVIDIA and with graphics and based on a few online educational content, I've kind of figured this out over the years. Okay, this is running from there. Okay, so what we're going to be working towards is the final render. So what we're going to be drawing as we go through the pipeline and see what happens is this scene. And this is just two like big quads, so two triangles stuck to each other. And there's two of them. And there's a simple checkerboard texture on them. And basically, wow, that's distracting. But this texture is just UV mapped onto the two quads. So the shader is not lit at all. It's just an unlit shader. So first, it begins with the CPU side process, which means everything begins on the CPU side, where you basically have your application and then a user mode driver below it. Can you still hear me in the back? Okay, cool, yeah. Sorry, I'm a bit distracted because of the music. But so your application will include your game engine, and like gameplay logic and so on. But how many of you have worked with OpenGL or DirectX or something like that? Okay, quite a few people, right? And I think a lot more of you will have worked with either Unity or Unreal Engine. So your application basically issues commands to the GPU, and we'll see what a command buffer is. But then below your application sits the user mode driver, which is this thing that's attached to your process. So below the user mode driver, there's the kernel mode driver, which is like the piece of software that actually talks to the actual GPU. So this stack looks like there's your application, and there's other applications. Like you might be running a game, and you might be running a web browser on the side, which might be doing some WebGL stuff. But there's only one underlying GPU, right? So the kernel mode driver is kind of responsible for time sharing between these different processes and allocating a little bit of time to from each process to the actual GPU. The KMD, the kernel mode driver, is also responsible for memory management, so managing the actual physical memory on the GPU. And it's also responsible for things like the hardware cursor. So when you move your mouse around, it moves really quickly, right? And sometimes your computer has kind of crashed, it's completely frozen, but your mouse still moves. And the reason for that is because that part of the code is actually handled in this elevated process called the kernel mode driver. So in your user mode process, what you build is a command buffer, which is this series of commands telling the GPU what to do. So a command can be like, clear the screen, you know? We had this blue thingy, so in the beginning, the first command would probably be, clear the screen with this blue color. Then it would be, let's say, we want to do depth testing, so turn depth testing on. Maybe we want blending, turn blending on, and so on. So these are commands that set GPU state. But there are also other commands which do dispatches. So there are 3D drawing commands. So you say, draw this mesh, you know, like once you've set the state, you tell the GPU, okay, draw this thing, draw this thing, draw this thing, and so on. So we'll be kind of focusing on GPU, like the 3D drawing aspect of things. Now, commands are sent in large batches. Commands are not sent from the kernel mode driver to the GPU one by one, but they're kind of connected into this major buffer, and that they're sent over this PCI Express bus. So if you've ever looked inside a PC computer, there's like a small CPU, there's some distance between the CPU, and then there's this big GPU that slots next to it. So the way they're connected is through this long, narrow pipe called the PCI Express bus. It takes a long time for the CPU to send things onto from this bus, and it cannot send a lot of data at the same time either. So it's think of it as a long and narrow straw that's going between the two. This thing is connected to the memory management unit, which is this hub which is connected to various sorts of memory. So the command buffer flows from the kernel mode driver through the PCI Express bus, through the memory management unit, and it's then processed by this specialized unit in the GPU called the command processor. What I'm talking about today, by the way, is like my focus is on NVIDIA GPUs, but all of this also applies to most other GPUs like AMD or, let's say, a console GPU or even the new Intel GPUs. Mobile GPUs work a bit differently. For some things, they're tile-based, which is outside the scope of this talk. But if you're interested, maybe Rupesh can help you out. He works on those. So anyway, these commands show up onto the actual command processor, and then it recognizes, okay, this is a clear command, this is a draw dispatch command, and so on. And so it dispatches them to the correct pipe. So pipe is like, it's again a queue of commands to process. So compute buffer commands can go into a different pipe, 3D commands can go into a different pipe, and so on. And finally, this is the VRAM, right? This is where you upload your textures or your meshes and so on. And when somebody says, I bought an 8 GB graphics card, what that 8 GB is video RAM usually. So let's look at the next slide, which is, now we've uploaded our meshes, we've cleared our screen, we've processed the command buffer to set the correct blend and depth states and so on. So now what we have is this basically mesh data, and it exists all the way in the VRAM in the beginning. And this data consists of a vertex buffer and an index buffer. And if you've worked with graphics, you've heard these terms before. So, but anyway, let's just look at what a vertex buffer contains. So this is just one quad, one simple plane we were drawing before, and we are drawing 2 of them. But it has 4 vertices. And each vertex has some data associated with it. So here we can see that it has some 3D world position given by X, Y, and Z. And then it has a UV coordinate. So how is a texture mapped onto it, right? You need some coordinates for that. And that's just laid out in memory serially like this usually. And then there's the index buffer, which states how are triangles formed from these vertices. So, and the reason that these are separated is because notice this vertex and this vertex are special. They're shared across triangles, right? So that data would need to be duplicated if we didn't have an index buffer. You would have to repeat that data, sorry. And in a bigger mesh, like a cube or even a larger mesh, one vertex can be shared usually on average up to 6 times. So that's a lot of repetition, so we want to avoid that. So the index buffer then tells you, okay, this is how they're connected. So 0, 1, and 2 forms a triangle, and 0, 2, and 3 form a triangle. So they're grouped in like 3 groups of 3. And so, sorry, I think I missed a small step before, which is the first step is the input assembler. So this phase of the pipeline takes each individual vertex and prepares it so that the vertex shader can run on this. So if you've ever written like a graphics application, you know there's a vertex shader, there's a pixel shader. What we're going to go through is how everything's connected between these concepts. So this thing picks up these vertices and basically distributes them so that they can be sent to be vertex processed. And the key with GPUs is parallelism. So you want to parallelize as many things as possible and do them at the same time. So you collect basically, what this phase does is it reads the index of the index buffer, it fetches the data associated with that index. It also checks whether you've already processed this index and if it exists in a vertex cache. And if it does, then you don't have to spend time running the vertex shader again. So then the vertex shader runs. And this is like this is the first piece of the pipeline that you actually encounter as a beginner. This is the first programmable part of the pipeline where you can write some code and it actually executes on the GPU. And that happens on this unit called the SM. This is an incredibly important unit of the GPU. AMD calls it something else, Intel calls it something else. So the names are going to be a bit different, but they all do very similar things across GPU vendors. NVIDIA calls this the SM. And supercomputing, so lots of supercomputers in the world run a lot of weather simulations and fluid simulations and sciencey stuff. And most of that, because they don't use 3D, they just use the math aspects of the GPU. So all of that runs on this unit. And as you can see, I don't know if you can see this from behind, but there are multiple of these. So I've kind of tried to draw a separate unit behind. So there are many SMs. And I took this architecture from NVIDIA's latest arch called Lovelace. So I looked at that architecture, I read their white paper, and I got the info out of that. But anyway, the vertex shader, what it does is it takes these individual vertices. Try to keep in mind what the inputs and the outputs of each stage are. So right now, we have no notion of triangles. We just know independent vertex points, which exist in space, and we're feeding them in parallel through this vertex shader. And the vertex shader, usually, if you've done any graphics programming, you will have heard of the model view projection transform and all of that stuff. So you take your object space, you apply a matrix, you convert to world space, apply a matrix, goes to view space, and then you apply the camera projection matrix and stuff as well, and you get 4-dimensional coordinates as an output. So there's quite a lot of like mysticism behind these 4-dimensional coordinates. I won't go into too many details, but you will kind of understand why we go into the 4th dimension shortly. But anyway, the output of this is called clip space, and that's all the GPU really cares about. It doesn't care about object space or whatever. So this vertex shader essentially is a mechanism to produce clip space coordinates, these 4-dimensional coordinates. And if you're into linear algebra, by the way, these coordinates, even though they are 4-dimensionals, they only have 3 degrees of freedom. So the rank of the vector, I don't know if that's a term, but it has 3 degrees of freedom. One coordinate, the last one is kind of correlated. But anyway. So in the vertex shader, now we've output these 4-dimensional coordinates. So now we are kind of getting ready to run the rest of the pipeline after the vertex shader. And so there's this invisible-ish step called the primitive assembly. So what we have now is we took our individual vertices, we ran the vertex shader on them, and now we still have individual vertices just in 4-dimensional space. So primitive assembly groups them. Now it reads this index buffer, and it now sees, okay, how are the triangles grouped? So we go through, like 0, 1, and 2 is a triangle, and so on. Now each triangle, this is the really interesting and like semi-mystical part of the whole process, which is, sorry, I have to change slide twice. Yeah, so the first step that happens is viewport culling. So in this 4-dimensional space, it's really hard to imagine. That's why I've drawn some diagrams here. So this is the W axis, which is X, Y, Z, and W. So it's the fourth component of the vector, and this is X. And the problem with this is like its 4 dimensions are impossible for humans to visualize. So I'm doing the best that I can. But basically in this 4-dimensional space, this is the visible region in the camera that the camera is seeing. Anything outside the region will never be seen by the final render. So if a whole triangle lies outside of the visible region, it can be just discarded. You don't need to process it any further and waste computation on it. So you just discard it. If it's completely inside, then of course it needs to go through. You see, the player will see the triangle. But if it's in between, well, it still goes on. So if it's only outside, is it fully culled? And this is called viewport culling. And the next stage is called clipping, and that's where the name clip space actually comes from. And it's something I had no idea how it worked until I actually wrote a software rasterizer over the past year. So if you can see this diagram, basically this triangle is, I've tried to represent it here. And we want to clip it because only a certain part of it is inside the viewable screen area. So it's literally like cut, like clipped, and multiple triangles are created from it. So it forms 2 triangles within the GPU's pipeline and is then passed onwards. So this clipping stage produces more triangles maybe than went in if it's like partially outside. The next is the projection and viewport transform. So now we have these clipped triangles that need to be processed. In this stage, we then divide the 4-dimensional number we got, X, Y, Z, and W, and we divide the X, Y, and Z components by their W component. This is called going into normalized device coordinate space. So another way of visualizing it is that these objects in this XW space get projected down. So this object kind of gets projected down onto the line where W equal to 1. This is just a bit of linear algebra. Like it's important, but it's not super important to know why it's the case. But what happens here is your coordinates, which started from like, the vertices could be anywhere. So the range was like -infinity to infinity. And after doing this projection, the range goes from -1 to 1. And then you just do a simple kind of addition and multiplication. And this is the interesting part, is that now the coordinates go into from 0 to the resolution of your screen. So this is super useful now. So now you processed a triangle, you did all of these calculations, you discarded all the work you didn't need to do. And now you have vertex coordinates in screen space, like in actual pixel space, which is very useful. At this stage, you can also do backface culling. So if all the triangles we describe here in the order, they're in anti-clockwise order. So if you view them from up front, it is anti-clockwise, but if you try to view this plane from behind and actually you see the winding, it becomes clockwise. But you don't need to draw things from behind because usually you don't see the insides of objects. So that's another optimization where you can just discard the triangle if it's facing away from you. And this is called backface culling. Now the next step is triangle rasterization. And it's coming up more and more in modern graphics programming, like understanding, like in nanite or in any like high triangle density graphics, you need to understand this step quite well. So what is rasterization? So up till this point, we've had like 3 points. Now we need to find out which pixels lie inside of those 3 points that define a triangle. So it's basically the process of converting vertices into pixels. But what you do here is you actually group things in, I don't know how well you can see this, but you actually group these pixels into groups of 4. So I've colored them so that you can understand. So for example, this is simple, right? Like these 4 pixels lie in the triangle, so they're grouped together. But this 1 pixel, let's say these 2 pixels lie in the triangle, but these 2 do not. But the GPU still rasterizes and shades them. And this is, you might get asked this in graphics interviews, so it's good to know why this happens. So to be clear, the GPU will rasterize pixels that are outside the triangle and will do extra work, which the GPU never does, if possible. So it's doing all of this extra work for a reason, and we'll see that reason later. But right now, just remember that it groups pixels into these groups of 2 by 2, and this is called a pixel quad. And the pixels which lie outside a triangle are called helper lanes because they help with something, and we'll see what in a sec. Also, if you have a large triangle, right, covering many pixels, that work of rasterization is distributed across multiple GPCs. And what is a GPC? It's this blue box here. So it contains many things. So a GPU is like a hierarchy of units. At the lowest level, there's the SM. Many SMs come together to form a TPC. You can think of it as a tree almost. Many TPCs come together to form a GPC. So when you buy an NVIDIA, I don't know, 4080 versus an NVIDIA RTX 4070, what's different is the number of GPCs usually. So it's kind of, 4080 will have more of the same units. The next is the early Z-culling. So what you can do is, when you're rasterizing a triangle, now what we did was we took the vertices, we converted them into the screen space thing, we rasterized them, and now you can still discard some work. So now what happens is that when, for example, in this quad behind, let's say this front quad has already been drawn. So these pixels in the quad behind will still be rasterized, but they will never be seen because they're covered by another piece of geometry. So what happens then is, it kind of, you can detect that in the depth buffer and just not run the pixel shader on it at all because you will be wasting work. This is like, you want to ignore occluded geometry. So this is where early Z-culling happens. This is a very complicated area. I think I won't go into it, but there are places where early Z-culling doesn't work, so you have to do it at the end of the pipeline, and that's called late Z-culling. And there's hierarchical buffers of Z, and there's a lot going on here. But I will skip that. It's just good for you to know that there's a lot of complexity in this area, and that you will need to read up on it yourself if you're interested. So again, why pixel quads? Now let's explore this. So again, we are looking at why we are processing things outside the triangle, even though we will never see them. And this is one of my favorite parts of graphics, which is digital signal processing. So let's say you have I'm going to start abstract and make it concrete in a second. But let's say you have a signal that's high frequency, but you sample it not enough times. So you kind of sample it once here, once here, once here, and you only see these points, right? You don't see the underlying actual function. What you can plausibly say is that the function was always this curve. Earlier, Shahriar also showed this in his talk on audio programming, but this shows up everywhere. So what this looks like in 2D is this, which is that the original image is this. If it's downscaled in a naive fashion, you get fake artifacts from it. Like you get these, moire patterns that were never there to begin with. And this is a problem that happens all the time, and it happens in different ways as well. So I've written a blog post on the various manifestations of aliasing, as it's called, or undersampling. And I could go into like massive amounts of like theory about this, but we don't have the time right now. But pixel quads help you solve this problem. So what the GPU does is, when you upload a texture for a checkerboard texture, for example, or a wall texture, brick, whatever, it will create smaller and smaller copies of the texture. But they're not just naively small. What we do is, for one pixel in this, 1 pixel in this is mapped to, let's say, 4 pixels in this or whatever, or 2 by 2, let's say. And it's like a blurred version and minified version. That's an easy way to say it. You blur it a bit, and then you make it smaller, and that helps you fix the problems. You're doing some DSP magic. You're getting rid of high frequency detail from it. So anyway, this is what the GPU does, and it does it up front. It does it when you upload the texture or when you request a mipmap refresh. But then the question remains, how do you select this mipmap? This is what it looks like with and without mipmaps, by the way. This is without mipmaps. And there's all kinds of random patterns emerging. And here it looks correct. Like it looks like it fades off and things average off as things go farther away. And this would look really bad in motion. It would be extremely distracting. Also, a general detail, this is not just MIP mapping, this is anisotropic filtering, but let's skip that detail for now. Just see the difference. And this is where the pixel quads come into the picture. So here, there are two quads, same quads. One is super far away or super small, doesn't matter. And the other one is really big. What happens is here, if you can't see this, there's a very similar pixel quad down there. What we're visualizing in the color, by the way, is, let's say, the U channel, like, you know, UV mapping. So we're just taking the texture coordinate of each of the 4 pixels, or every pixel in the fragment, and we're coloring it to give you a visual idea. Here, what the GPU will do when you sample an actual texture is it will look at how much the UV coordinates are changing in that pattern. So in another way, like, it goes from, let's say, pretty white to pretty orange here. So it's a larger change. But there, it goes from basically white to, you know, basically white, just a little bit more orange. So there's a much smaller change in UVs here. So it can kind of deduce that you need a larger copy of the texture here. But here you need a smaller MIP map. So that's what these are for. And this question comes up in interviews all the time. So it's good to know. Another byproduct of this, and why this is important, is because nowadays games are moving towards higher and higher polygon densities. So you have more geometry, you have more detail everywhere. And as your triangles get smaller and smaller and smaller, let's say only one triangle will be covered by 1 pixel only, but you will be shading 3 more pixels just to have this data. So it's a lot of wastefulness. It's called pixel quad occupancy. It's just good to know. And that is why pixel quads. And all of this happens in a different unit, by the way, which is called the raster engine. Now, let's look at how things are scheduled. So these warps are, these pixel quads, so groups of 4 by 4 pixels, are combined together into packets of 32 pixels, so 4 warps. And they are grouped together and they're put as a work bundle. So, you know, groups of 32 pixels, and they just sit there waiting to be scheduled. So this is warp scheduling. So what happens is the GPU scheduler now will pick up one of these 32 pixels, like these bundles, and will send them to the SM. So now your pixel shader runs. So this is the second programmable part of the pipeline. So let's cover some details about the SM now. I only have 10 minutes, so I'm going to speed through a bit. The GPU is a parallel computer, so it executes the same instruction, but on different pieces of data. So now, while it's processing these, say, 32 pixels, there's like a float A equal to B plus C operation, just an addition operation. What's actually going to happen is it's going to load across 32 pixels, the A value in all of those pixels is going to do the same for, it's going to load B and C for all of these pixels. It's going to add them up and store them into the A register. So all of this happens in one instruction, let's say. It's really fast. And all of this whole thing has one program counter, which means unlike a CPU thread, which has, each thread has its own like program counter and like it knows where it is in the stack, the GPU has a shared one. It does only the same instruction. Which leads us to branch divergence. So let's say you're running a pixel shader on 32 pixels, and half of the pixels take one branch. There's a branch in your code, so half of them run this code, and the other half run the else statement, and they run this code. what actually happens is the GPU executes both code paths. Like it'll go through if, and then it'll go through else. And the data will just be kind of masked out. But you're spending more time, and this is called branch divergence. And this is why you should avoid if-else statements in your shaders, but only if they diverge. If all of your pixels are going to follow the same if or else, it's fine. It's nearly free. And now we look at texture sampling a bit more again. So now you're, like your SM, now you do a texture sample in your pixel shader, and now it basically determines based on this pixel quad situation which MIP map to sample. It sends that to this texture unit. Texture sampling is an extremely slow process, and let's look at why. It might be a bit hard for you to understand in this screen, but when you magnify a texture, here it's like it looks very blocky. It's called nearest neighbor sampling. It's like when you zoom into an image in Photoshop, everything looks very blocky, right? Versus what you actually want is you want it to be smoother. So this is smoother. I don't know if you can see this on this display, but so for it to be smoothened, for one texture sample, it actually needs to sample the actual texture 4 times, and it needs to do extra math on top. And that's just for 1 pixel, but you're actually doing 32 pixels at the same time, so that's 32 multiplied by 4, and each image has, let's say, 3 or 4 channels, so that's another multiplied by 4. So when you do a texture sample, it takes a very long time. And it might not exist in the texture cache. So it might have to go all the way to the L2 cache. And if it doesn't, you haven't read it recently, then it's not going to exist even here. So it has to go all the way to video RAM and fetch it back, and it follows the whole path back. So it's a very, very long operation. And that's why you should really avoid texture samples in pixel shaders if you can. But the GPU has a trick up its sleeve. So what it does is that while this one warp is waiting for its texture to come in, it's like a waiter, right? It takes the order from one table, conveys it to the kitchen, but then it goes to another table and asks them for their order. So it'll just pick up another warp of 32 pixels and assign it to the same SM. And then the SM just continues executing the logic, and maybe these 32 warps then ask for a texture read. So then it'll pass that on, and then it'll check, okay, has any order come back from the kitchen? So basically the texture unit, and if it has, it'll kind of resume executing. And this is called latency hiding, and it's one of the big reasons why GPUs are as fast as they are. Like without this, it just would not run this fast. And now we go to one of the final slides, which is the output. So this is where, until now, we kind of spread out all of our work into, over the GPU. Now here we serialize it again. So we sort it. And why do we sort it? Because blending is order dependent. So when you blend things together, it cares usually about what order things came in. You can't just like do things randomly. So first you sort all the incoming warps by their primitive ID, and then it goes through this unit called the ROP, and then it writes it to the final texture so that it can be displayed on screen. So we kind of just went through the whole journey of how, how these 2 triangles got rendered. And that was a lot of stuff. So let's kind of recap. We started on the CPU. It sent some commands to the GPU. The commands travel over the PCI Express bus, went to the memory management unit, and then the command processor. And then we picked up individual vertex data from it. And then that was our input assembler phase. Then we ran the vertex shader on it, on this SM unit. Then we did primitive assembly. So we took these individual vertices, grouped them into triangles, and then we called the triangles which were completely outside the screen. When triangles were partially inside, we clipped them to form more triangles. We did projection transform to convert 4D to 2D. Then we viewport transformation to convert it to the actual screen resolution. Then we ran the rasterizer. We picked up extra pixels even outside of triangles called helper lanes where necessary. Then we did an early z-pass to discard things which were already under something, so there was something on top already. Then we ran the pixel shader, which is what you do on shader toy or any kind of, that's where the bread and butter of graphics programming is when you begin with graphics programming. And then finally it goes through the output merger and the render output unit, the ROP, to render this onto the actual texture, where at some point it'll go through to the monitor, and then it'll go to your eyeball, and then to your brain, and then you'll see things. So that's kind of my talk. Do you have any questions? If we have time.
Yeah, we can take 4-5 questions.
Yeah, you. Sorry. I'm sorry. You can have it later. Yeah. Yeah. Okay, so he's asking, you said that beware of texture sampling. Is there a better way? The answer is yes and no. Like, texture samples are essential to graphics programming. Otherwise, you wouldn't have nice graphics. The key is to not use them willy-nilly. So sometimes artists will sample the same, especially in shader graphs, artists will sample the same texture like 4 times. Instead, maybe sample it once and keep it in memory. Another thing you can do is pack, if you're like, if you can pack many texture, if they're single channels, into one texture, maybe you can do that. If you can pack data into tighter channels by hiding more data in the same information, maybe do that, like half precision and shader tricks. So that's kind of what you can do. But the base thing is just keep an eye on like shader graphs and like a ridiculous amount of samples, which is where I think complexity happens most often.
Okay, I have one more question. Okay, this is when you're explaining about this picking that right LOD level, MIP map. So here the GPU will not consider that camera distance or anything. It will only consider the UV coordinates there.
Sorry, I did not understand.
You said that how GPU will pick that right MIP map level.
Yeah?
Yeah. So here, let's say that ideally the procedure is that, let's say from the camera it is whatever the farthest triangle, we'll pick the lowest resolution, and from the nearest one will pick the best resolution.
Yeah.
How GPU will ignore these things and will only consider the UV coordinates there?
I don't fully understand the question. Yeah? No. Camera distance does not matter, but when you actually execute each pixel, right, like the pixel shader, it will kind of interpolate UV coordinates. So you get UV coordinates. Actually, I have a slide on this quickly. I won't spend too much time on it. Oh, shit. Sorry. Anyway, sorry. There's too many screens here to keep track of. But basically, if you've seen a hello triangle with one red corner, one green corner, and one blue corner, and it changes color in between smoothly, right? So there's an interpolation stage that happens after the vertex shader where you interpolate the outputs of each vertex across the triangle using barycentric interpolation. So that happens in that stage automatically, is where it computes the UV coordinates. And that's how it chooses the UV map. Oh. If that doesn't answer your question, we can talk about it later, maybe.
Yeah, sure.
Yeah. Does anyone, maybe, yeah.
I'm an Unreal Engine developer.
Yeah.
Game developer. So I'm interested in this part. So what kind of resources like books or documentations you recommend for, this is a lot of technical stuff.
Yeah.
So how can we start and get good at it?
So I think like if you want to get into the deep end, Fabian Giesen has a post called A Trip Through the Graphics Pipeline. It's 10 years old and it's quite difficult to read, but maybe read that. Or NVIDIA has a thing called the Life of a Triangle, which is also quite vague. You can look at that. Or actually NVIDIA has talks during their GTC conference every year, and they're quite hidden and you need an NVIDIA login and so on, but they're quite good. And you can find good talks there, I think.
Thank you, sir.
Yeah. Anyone else? Maybe there? You can just stop me, whatever. Yeah.
Uh, where does batching comes in the process of in the
Yeah.
pipeline?
So batching mainly comes in from the CPU side. So it's a CPU optimization before things even go to the GPU. It's more like you're telling the GPU, okay, draw one mesh, one quad. Okay, draw another quad. Okay, draw another quad. Which, if you're drawing like a million quads, it takes a very long time, or even like 1,000, right? Instead, what you can do is you can tell it, okay, draw these 1,000 quads. It's like one instruction, and you upload a buffer with some instance data and so on, like telling you where to draw them and so on. So there's a bunch of things there, but batching is primarily a CPU optimization where you tell the GPU less, so less information has to go over that narrow PCI bus, that narrow straw between the CPU and the GPU. Any more questions? Maybe he has one last and then we call it.
Can you shed some light on how DXR pipeline works and differences? DXR, DirectX ray tracing?
Yes. So,
Yeah, so
yeah, I have very little experience with ray tracing, but it's substantially different. So that's one thing I kind of omitted from the talk is like this talk only pertains to the old school pipeline, which is still used a lot. It does not include ray tracing, which most of which actually happens in different units. Especially the ray intersection stuff happens in different units. But I can't speak to that super well, basically. I haven't worked thoroughly with DXR, but there's also other parts of the GPU that I haven't covered, like tensor units, where when you do machine learning inference, these are like systolic matrix multiplications and addition, which also run on different units. So graphics, I see it as it diverging a bit. This is not answering your question, but just a rant. Graphics is diverging. We began in a simple place, and now we're moving towards something where there's ray tracing, which is like, I think real-time ray tracing is on the horizon. There's machine learning stuff like NERF, where you just shoot a virtual ray and run a machine learning inference, and it just gives you back the result of the rendering equation and stuff like that. So, and there's mobile chips which work in a completely, slightly different way. And because they have different power constraints and so on. So yeah, I would guess though that once you have this foundation, you can now look at the DXR documentation and it'll make a lot more sense if you go look at it.
Just to complete the picture,
Yeah.
let's say if someone wants to generate the checkered texture using compute,
Yeah.
where does it stand in entire pipeline?
I mean, I wouldn't actually run it using compute.
Sure.
Instead, I would run it in the... That's a good question. I would run it in the pixel shader, I think. Because in the pixel shader, you have access to the UV coordinate. And based on that, with some modular arithmetic, you can define the... Or were you trying to ask a different question, maybe?
I was trying to ask, where does the compute pipeline fits into all this?
Yeah, that's a good question. So the compute pipeline ignores a lot of stages that you saw, and it only runs on the SM. So it's I think of it as almost maybe even a strict subset of graphics. Maybe I'm wrong somewhere, but I think it's a subset of this, and it only runs on the SM. So in a compute shader, you can request resources from the texture unit or from a VRAM or whatever, like just as data, which is not interpolated. So then it'll take the L1 cache, L2 cache, and then VRAM path. But otherwise, it's very similar. It runs on the SM, and it ignores your polymorph engine and your raster engine and so on. Yeah.
Any more questions? One last question.
Hi. So we had this warp scheduler, right?
Yeah.
So warp scheduler does for pixel shader. So doesn't it work for? I mean, doesn't it do scheduling for vertex shader?
It does indeed, but the thing is, texture operations in vertex shaders are rare. That's why I didn't mention it there. It's a really good question though. So sometimes you want to do texture-based height map displacement or something in the vertex shader. In that case, it works the exact same way. Also in compute shaders, if you request piece of memory or whatever, like it needs to wait on, it will go into a dormant state and it will pick up a different and schedule a different warp. But yes, also compute warps are also executed the same way.
Okay. Thank you,
Yeah.
Apoorva, for a wonderful
Thanks a
talk.
bunch. And thank you for Rupesh and for all the organizers and folks here. Yeah.